Kind of related to that, do you have, I know a lot of students here are becoming aware of additional resources that the partner organizations here provide, and are thinking about, maybe we should, either they themselves or their PI should start writing some allocation requests. Mm-hmm. I know also, I think you, at least Tom, and I suspect some of you others may have actually reviewed allocation requests from time to time, from people who are interested in using your systems. Do you have any suggestions or tips for students who are maybe approaching this for the first time? What should they include? What should they not include? What are the keys to writing a successful allocation request?
Don't trust your PI to do it right. Make sure you have timings in there and a well-justified set of resources you want to use and the time that you'll need to do that, and double it, because it might get cut in half when you get allocated. Is kind of the standard things. And then back to your centers discussion, having a well-balanced center that can support researchers broadly is really important for keeping PIs on the campus and for recruiting new ones. We've had people leave my university and beg to use us still, and we're like, no, you've left. You've got to use what you got now. So,
please fill in all of the fields that we ask for. Please do that. I've done a lot of the technical reviews, and I always really try hard to find the information to give a high score. You've bothered to submit the thing, but sometimes people make it really hard. They're just oh, whatever. No. There's lots of applications. It's not a given that will give you something as much as so please do put in effort and don't just be oh, whatever. It makes me sad when I see that, because no, I really want to give you this time. Make my job easy.
I'll say it's not just about the science. Science has to be in a proposal request, but it's mostly about how you're going to use the computational resources and why you need them.
And going back to something we talked about earlier, ask for help if you're on the side of applying, because I was in a little bit of a panic when I became a professor and realized I had to make all of these decisions on my own, and it's not on your own. I contacted so many professors, some other people I worked with in grad school that had got positions around the same time, and we kind of worked together to think through these things. So don't just try it on your own. Make sure you even the people in this room, I probably contacted someone I met when I was a student here. So just use your available people resources too.
Yeah, and also check out if there's any other opportunities other than going via your PI. We have, for example, recently introduced a student project, so students can now apply for their own resources. They're quite limited, but it's still quite a lot. So some centers might offer this opportunity, so check out what they have on their websites.
Thanks. You, I guess both you, Tom and Michelle, mentioned earlier that one of your big challenges is dealing with version issues and just trying to kind of keep up to date as clusters update various packages and you need to rebuild codes and such like that. And I know this is one of the big challenges of our field, is that it's moving very quickly, anything from just software updates to new technologies. What are your tips for kind of how far to chase that? Is there a point at which you should maybe kind of stop or get off at least the optimization train because maybe your code is good enough, or the return on the time you're investing isn't really there anymore? Is it just the nature of any scientific research that's using HPC that we need to just kind of continue to push and use the latest and greatest? What tips do you have for when to keep putting in that time for technical improvement and when to maybe give it a break?
I mean, if you get your science done, the performance isn't necessarily that important, as long as it doesn't take 10 years to do the calculations or something if you're a student. But yeah, optimization never really stops, but you don't have to necessarily have it the perfect code, the perfect performance to do what you're trying to get done.
Yeah, I kind of think it's sort of the same with anything when you're on working on a project, is that perfection is the enemy of good. And so it's well, how much do I need to polish this paper? Or how much do I need to add more data to this project? No, just a little bit more. And I've seen people there's this one lab I have in mind that gets scooped time and time again because the PI can't let go and just publish. And so it's a real shame for all the postdocs and PhD students in the lab because they don't get these papers. And so if it's doing a good enough job, like you're saying, and, you know, it doesn't have to be perfect. It just has to be good enough for you to do what you need to do. And, you know, sometimes that goal will change a little bit. So you're like, oh, it's not good enough anymore. We better do a bit more optimization. But don't get stuck trying to be a perfectionist if possible.
For me, the things that I abandon the most are actually going, not when I'm chasing the latest and greatest, but usually if something's a little bit outdated now. So sometimes I'll read a paper and maybe it's just a year or two old in machine learning because things move so rapidly there. But then they probably started the project much earlier, so then they were using much older versions, and I'm fighting to get a bunch of old stuff up and running. That's the times where normally I'll try, and then I'll kind of quit and be like, well, we can still take the ideas from this paper, but we can go off of maybe some newer stuff that's been done and try and go from there. Because trying to get old stuff up and running and struggling is usually like a losing battle because it's just going to become more and more outdated.
Yeah, I think I've also seen the most struggles happen when you try to optimize too early. So you haven't even gotten it running, but you try right away from the beginning to make it as good as possible with everything you have learned, put everything in. And then it's often our job to then be like, okay, let's take like 2-3 steps back. Let's start first, make it work. And then we see what we can do. And depending on how much time there is, how much pressure from the outside, is it your own project? Is it for someone else? Then we see how far we can go with the optimization.
Yeah, and Python's a great rapid prototyping tool that has a lot of existing libraries and code bases that you can steal things from and not have to rewrite. When I was a student, we did not have those things, so it was much harder.
Here at the summer school, we certainly, you know, for example, the 2 tracks we just did, you know, very helpful for students that are, you know, jumping in and maybe starting to write their own code base or starting with a code base that's relatively recent. But there's also the case sometimes that students come into labs and are using legacy codes that maybe have been around for a long time. Do you have any advice or suggestions as to how students can maybe try to integrate either optimization approaches or modern software engineering packages into codes that are relatively mature?
I have a very mature code. It's one of the first community codes, and it's done by a large team, and we're constantly optimizing it and fixing it with the various versions. So we do want to make sure the results are the same, but that often can't happen. We love the GPUs because they're deterministic. If you put in the same parameters, you get the same results, or the GPU is broken. We can use that to test the GPU, which is very nice. Optimization is the question if you need it for the science. And even the mature codes, we were originally Fortran 77. Now it's a mix of C, Fortran 77, Python, CUDA, AMD GPU code. It's a whole mix of things, and they're actually difficult to penetrate.
I feel like I should say something about this, but I haven't quite collected my thoughts because when I did my postdoc, I inherited a very established old code base that was in Borland C. I didn't know there were go-to statements in the C programming language. And it was really challenging because they definitely needed optimization, but they weren't in an environment where I could apply any of the tools that I had learned in graduate school. And so for me, the biggest win there was just educating the group, because I was the youngest person in the group and a lot of them hadn't had exposure to more modern tools. And I did not succeed in a lot of the optimization I wanted to do when I was a postdoc, but I planted seeds, and then I was even on a paper just last year where they actually finally ended up doing something that I had proposed, like I think in like 10 years ago. So I don't know if that's a win. I don't know if that's a suggestion, but at least make sure that your group, your PI, whomever knows about the potential like gains if you're dealing with an old code base of modernizing some pieces of it.
And I'll add, if it works, don't think about doing massive optimization or rewrite. So for example, in Amber, there's a tool to build the input files effectively. It's been tried to be rewritten by students 4 times. They never got the right results, and they just threw it away. We're about 20 years later, finally have one that actually works and is extensible. But I lost 3 years in graduate school basically doing code optimization and MPI stuff. It takes a long time to do this. But I learned a lot. You don't learn coding except by coding. You got to do it, and not just homework. For a class, it's got to be a real science problem.
You're mentioning that, Tom, that they tried several times and kept getting the wrong answers. Maybe think then that you probably have pretty good tests in place so that you know if they're getting the right answers or not. And I was wondering if more generally, you four could speak to kind of the topic of testing. How have you integrated into the codes that you use? How have you found it useful? Again, kind of what is a good level of testing to implement? Because that's one of those things where you can kind of always more tests you could write, right? But how do you know when you've maybe gotten to the right point?
Well, for every new feature we put in, we require a test, basically. So there's a lot of tests that take hours to run, but they're kind of critical.
Yeah, and we have integrated into a GitHub workflow. So whenever we push to main, the test is running, and only if that succeeds, that implementation actually makes it to the main branch. So that's also a good way to protect it a little bit automatically.
I'm going to ask you, Sarah, just because you're the containers person. Your thoughts about testing in the context of containers. Do you think that is a pretty useful way to try to implement kind of CI for complex pieces of software? Just, I'm curious about your experience with that, or what you've maybe seen other people use.
In terms of like continuous integration, or
Yeah.
Yeah, you can do that with like GitHub Actions, where you update the recipe and it like pushes the container, which can be quite good. Yeah, I do think it's probably good to have a test case for your container to make sure it's doing what you think it's going to be doing. As my old wet lab PI would say, you always need a positive control. So he's obviously talking about like running a PCR or something, but it's the same for really anything you're doing. Having unit tests, I think, is important, because you never know where something weird is going to come in. Like, you just can't predict. Yeah, so it's worthwhile doing that type of thing. I haven't actually observed a lot of it myself, though. But maybe that's because I'm not a research scientist anymore. I'm like, here's a container, or you should use a container. Here's how you do it. Good luck.
I think sometimes the containers can have trouble with the drivers for like NVIDIA drivers or accelerator things, so that's a challenge to get them working sometimes.
Saw one go by earlier, and so I apologize if I'm slightly misquoting it here. But it was something along the lines of, do you have suggestions for ways to communicate the HPC work you've done when oftentimes many of your collaborators and many of the conferences you go to are focused on your domain science, right? So these are people that maybe aren't as familiar with your HPC techniques, and so even though you may have spent the last 6 months carefully optimizing your code, it can be difficult to share that with a domain science audience. Do you have any suggestions on how to kind of communicate effectively with them, both the scientific results, but also make it clear that there is a lot of HPC and knowledge and experience that went into achieving those results?
Well, there's specialized meetings like supercomputing and PERC that we have in the US that you can have those kind of presentations at and present. And in my domain, science, there is a lot of people that present on the codes and the results and analysis. But I'll say that at my university, we have free research computing resources, and there's groups that don't know this throughout the campus, and they go to Central IT and get these stupid information about what machines to use. And when they could have just come to us, so we're constantly evangelicalizing what's available and what's out there. You know, if they by mistake go up into the cloud, all of a sudden this huge bill comes in and they're like, ooh, I didn't expect that. So it's really raising awareness. This is why I remain involved in this CART group, because we're trying to advocate for research computing and data on our campuses and all the various roles that people play, from research software engineers that we talked about yesterday to the systems people to the networking staff, security.
This is a problem for bioinformatics, that like there's people that do the computational aspect, there's people that kind of do a bit of wet and dry lab, and there's some people that are like purely wet lab and they don't really understand anything about computational stuff. And so I think if you're presenting to those groups, or even people in your own lab, you know, they might not really understand or care about the computational aspect, that's fine, you know, but explaining to them kind of what's the importance of it, what's the bottom line. So they don't know or care about like, well, I did this dependency, or it's just like, I did this, now we can run it X times faster. And they'll be like, oh, wow, like what's the result? Not necessarily how you got there, because that's all Greek to them, or you know, it's not their interest. You don't necessarily want to know about how they grew their cells. What percentage media did they use? You don't care. That's fine. You know, you have different interests. That's good. But yeah, what's the bottom line? Why should they care? It's kind of the same when you're selling any idea to someone. You know, what's in it for them?
Yeah, I have the same advice for my students. I tell them when we're talking to the domain scientists, you know, they just honestly don't care about your computational trials and tribulations. The only time you might really need to communicate that is if someone's questioning your work or something. But I don't see that normally happening. But also, as you were saying, there's conferences and sometimes there's journals. So in the nuclear field, it's fairly low impact journal, but nuclear instrumentation and methods, and there's kind of two sides. It's like if you build something, you want to talk about technically some device you've built, or a computational method or approach you've taken, you can publish it there. It's actually really widely read. It's just not a scientific result. And so there's places to publish, there's conferences to go to where you can have those conversations. But yeah, I don't think, at least for the work that I do, we don't need to always be communicating how hard we're working on all of these technical details to the domain scientists, because they really just want to know if it's useful for them.
What do you see as kind of current trends that are going on, things that maybe students should be aware of, you know, whether maybe it's a specific new technology or maybe it's just a certain approach, certain paradigm? Are you aware of anything that is maybe specifically affecting your work or that your group is making sure to stay on top of?
Well, we are a little bit behind there, maybe behind UK especially, and Germany and so on in the Nordics. So the research software engineers is a quite new concept there, but I believe that's something that researchers will really benefit from. Having research software engineers in the research groups, support not necessarily writing code for them, but also supporting them writing better code, writing better performing code. So I think that, yeah.
I appreciate your honesty, Tom. We're coming near to the end of our panel time, so I wanted to conclude by giving you just kind of each an opportunity to give a few concluding remarks. And so think of this as maybe some advice you'd give to students who are, you know, dealing with HPC challenges with their own scientific work. Maybe it's a specific tool you've suddenly thought of that is really useful, but I haven't asked you a good question so you could tell people to use it. Kind of whatever comes to mind for you. But I just wanted to give you an opportunity to give some closing thoughts.
Well, I didn't get to talk about the challenges before.
Oh, you're right. Yeah. No, you didn't. Yeah. Why don't you tell us?
So I want to say that it does not always have to be like OpenMP, MPI, and this kind of stuff. Like in my work, we work mostly with embarrassingly parallel problems, and it can start from something like using GNU Parallel to parallelize these things, and that can even be not even own code, but it can be programs that already, a software that already exists. And then you notice at some point that this is maybe not enough anymore. And then you go one step further, you look into your code, what can you do? And I think for some researchers, it's quite scary, this HPC topic, but when you take like small steps into it and look what is out there and look at, for example, curriculums of courses to see what is actually out there. I think there was also a question there, like how do you know what you don't know? Course curriculums are a good checklist where you can see, okay, I know this, oh, what is this actually? And then you can go and either visit the course or find some other resources about it.
I think my advice is that you're capable of learning everything and anything. So just because you get your PhD using one particular type of technology or tool or programming language or whatever it is, that doesn't mean that that's just your expertise that you're stamped with and you carry through. I definitely got my PhD thinking, okay, I'm a CUDA programmer, that's my expertise, I'm just gonna go around and get jobs where they need that. But the world evolved and I evolved with it. So yeah, don't think that you can't grow and evolve as well.
Yeah, and I'd say, like the embarrass and the parallel, there's tools that have emerged that you don't even have to know Linux or command line. You can just go into a web-based interface and get jobs submitted to the computer without having to learn Slurm, like Open on Demand in the US, and Jupyter Notebooks that you can enable to test out your workflows and so forth. And I'll say a funny story is about the embarrassingly parallel is in the US for a while they were penalizing people who were doing embarrassingly parallel work because it wasn't scaling to the whole machine. Well, it perfectly scales to the whole machine actually because it's embarrassingly parallel. But we convinced them the science is good science. It doesn't have to be full scale parallel across the machine with an MPI job. Different ways to do things.
I always thought it should be called awesomely parallel because it's so easy to parallelize. Why is it embarrassing?
There was actually a movement for a while to call it pleasingly parallel, but I don't think it ever really caught on. But it was, yeah, all the people who were writing software tools to help with these kind of workloads, they were like, we're not embarrassed, why should you be? Yeah.
Yeah, I totally agree with that. That's fantastic. And yeah, I don't think you don't have to use MPI or something like that for work to be valid or for the scientific output to be valid. Like I would suggest against oh, well, you use this. No, they're doing good work, probably. And also that the landscape will continue to change and you will continue learning and growing and shifting. So you're never done in terms of upskilling and learning. I think that would be my main takeaway. I never thought I'd be presenting at a supercomputing type of conference when I enrolled in my human biology degree. Totally unexpected. And so you never know where you'll end up, but being adaptable and keeping, just at the risk of sounding super cliche, keeping an open mind is important.
I'd also say if you're a small institution, look for other bigger institutions in your state that you can go talk to and ask for resources. So in Utah, I'll let researchers at different universities in the state use our resources for free. And until they start using too much, then we make them pay. But we support Utah State up there. They use about 10% of our cycles, and they're now paying for it. And it's great. And the communities out there are great for supporting research, computing, and data. Great to get information to help you along, get you started. A lot of people who've learned, like Michelle, how to build a cluster want to let other people take advantage of that knowledge.
Yeah, I thought of one last thing, and that's just if you're talking to people across disciplines, as we do here, I think it's important just to stay open. I've been in a lot of such situations where people say, oh, you're not using this, you need to use this. Like, we use it in bioinformatics. I can't believe you don't use it in physics. And I was like, well, what about this? I think you should use this. And it just becomes like people telling each other what's best for a field that they don't know anything about. And so I think like these are great opportunities to listen. The challenges are so different across disciplines, and be open. So learn what there is out there, but don't force your ways upon others, or try to.
Well, I really appreciate the four of you being willing to come up here and sit in the hot seats and answer these questions today. I know that many of you asked questions that they didn't have a chance to answer up here, but the good news is they're here all week. So please, if there are other things you're curious about, I encourage you to come up and find a time to chat with them. We're also going to have another panel on Friday. The focus of that one will be on the future of HPC. So that will be another opportunity for you to be able to submit questions and get them answered by experts that are looking ahead to future directions. So thank you very much for participating. Let's have a round of applause for our panelists.